All right, so let's get into a little bit of a derivation here of the mutual inductance, something called the mutual inductance. It's important to understand what the mutual inductance is and where it comes from. And so I just want to talk a little bit about this circuit, kind of what we're looking at here. This is what I showed in the previous slide, but I made my own figure here. This is from the Eulaby textbook. And what you'll see is that they basically have a voltage source driving an inductor. There's a lot of extra stuff going on in this, so when I do the derivation, I'm going to go out of here. But you see that this coil is kind of wrapped around a core, and so we can assume that current's flowing, this direction through the core. And so using the right-hand rule, we can see that the flux, the magnetic field lines, are going to be coming out, and this one's going to be going clockwise, and this one's going to be going counterclockwise. And this one sort of links the first coil to itself, right? It's not really linking any other coils here. It's just coming out into the air around this coil and coming back. But this second one, it links the second coil to the first coil. This coil here that we're going to I'll call this one L2 and I'll call this one L1. I'm actually going to just move into a separate slide here when I do this derivation, but I just wanted to talk about this circuit a little bit first before I redraw it. And so what the caption shows us here is that current in I1, so basically this current, or current in L1, this current I1, it induces this flux, this magnetic flux, phi 1,1 and phi 1,2. And phi 1,2 is what induces a voltage V2, right? This, if you take the magnetic field lines out of this circuit here, and you didn't know it otherwise, you would be inclined to believe that nothing is going on in this right-hand side of the circuit because they're not connected. Up to this point, all we've seen are electrical connections. Like I talked about with the resistors, if I don't have an electrical connection between these two inductors, nothing should happen. But because we now need to account for magnetic coupling, something is going to happen. I'm going to get a voltage induced V2 across this second coil as a result of magnetic coupling when I have a current I1 flowing through L1 here. Okay, so that's what we're going to talk about. That's what we're going to derive. And so let's go ahead and let's just redraw the circuit, but we're going to scrape away some of the details here. I don't want to show the dots and all that and the cores, so let's just draw our own circuit here, and we'll just derive it. Okay. And so we want to show how we're going to get a voltage V2 here. So we got V1. That would be pretty obvious. That's going to be the voltage across my first inductor. But how in the world are we going to get a voltage V2 here? So let's draw our current I1. Let's label these inductors. Let's call this one L1 and this one L2. And then let's draw some flux lines. I guess I can use a different color. Let's use something like dark green here for the flux lines. So we'll draw this one linking these two coils, and then we'll draw this one just linking back to the first coil. And we'll call this one flux 1,1 or phi 1,1, which is the flux linking the first coil to itself. And the second one we'll call phi 1,2, which is the flux linking coil 1 to coil 2, okay? And so the total flux through L1 is the sum of those two fluxes. So we'll say phi 1 is equal to phi 1,1 plus phi 1,2. Okay? And so we can define something called the magnetic flux linkage, uses the Greek variable lambda here, flux linkage 1, as the number of turns of coil 1. So let me say that this coil has N1 turns and this one has N2 turns. That's kind of given in the figure here too. I didn't talk about that, but obviously you can see that they show these two coils have two different numbers of turns. It's not essential that they have different numbers of turns, but the N is part of the derivation here. So the magnetic flux linkage, lambda 1 for coil 1, is equal to the number of turns of coil 1 multiplied by the flux linking all those turns of coil 1. So in that case, it's going to be phi 1, right? Because it's the sum of these two fluxes that are the flux of coil number 1. Okay, so phi 1 here, phi 1 here. So if I wanted to define lambda 2, or the flux, or the linkage, magnetic flux linkage for coil 2, it would be the number of turns of coil 2 multiplied by the flux linking coil 1 to coil 2, because the only flux that I have through L2 is phi 1, 2 here, right? Okay, so that's my two magnetic flux linkage terms. I can define the self-inductance, or this L1 that we know is the inductance of coil 1. That can be defined as the flux linkage divided by the current that induced those magnetic flux lines, okay? So lambda 1 divided by I1. And finally, I can define the voltage, V1, which is equal to VL1, right? The voltage across inductor 1 in this case, as the rate of change of lambda 1 with respect to time, okay? And so this is where I kind of do some rearranging here. Let's rearrange lambda 1 from this part of the derivation. Lambda 1, if I multiply both sides by I1, you'll see that I get L1 times I1. So let's say lambda 1 is equal to L1 times I1, okay? And so I can say that this is equal to dL1 times I1 dt. And that makes sense, right? L1 is a constant, so if I pull that L1 out, I get that V1, or VL1, is equal to L1 times di1 dt, which is exactly what we already know, right? That's the voltage of my inductor is equal to the rate of change of the current through my inductor multiplied by the inductance. So that shouldn't be surprising. But what about V2? V2 is equal to the voltage across inductor 2, and that's also going to be the rate of change of lambda 2 with respect to time. So we can write that as d, I guess I already wrote that, but it's going to be N2, which is a constant, times d phi 1, 2 dt here. Of course, I could write that L2 is equal to lambda 2 over I2, but we don't know I2 yet. There's no I2, so this is basically useless for us right now. There's nothing connected to the load here, so the current flowing in this circuit is 0, right? I2 is 0, so that would mean that my inductance would be infinite. So this is meaningless at this time in the derivation. So I kind of need to stick with what I have just from the first coil here that's inducing flux from L1. I'm not getting any contributions from I2 here because this is an open circuit. So we'll talk about that in the next couple videos when we get to deriving this the other way, where I have the source here and this is open, and you'll see that it's going to end up with the same result. But for now, we can't write L2 in terms of I2 because we don't know I2, or we do know I2, in fact it's 0. Okay, so we need to stick with what we're doing here. But we want to write an expression for the voltage V2 that makes sense to us. Right now we're looking at number of turns and, the rate of change of this flux, not super satisfying. But what we can do, because we know that this flux was induced by I1, we can rewrite this expression as N2 times d phi 1, 2 di1. So the rate of change of the flux linking coil 1 to coil 2 with respect to current 1 multiplied by di1 by dt. And you'll see that di1 and di1 cancel here, which gives me right back to where I started. But if I keep it in these terms here, this looks really similar to my expression for V1, right? I've got some term multiplied by di1 dt. Here I've got some term multiplied by di1 by dt. So to keep units correct, we know this is in units of henries. This term here would also have to be in units of henries. And so this term right here that I have bracketed, that term is called the mutual inductance, linking coil 2 to coil 1. Okay, so M21, my mutual inductance here, is N2, the number of turns of coil 2, multiplied by the rate of change of the flux between coil 1 and coil 2 with respect to current number 1, okay? And so this looks incredibly complicated. And we're not going to need to derive this in this class. I'm deriving it just so you know where it comes from and what the heck the mutual inductance is. It's basically I don't want to say an imaginary inductance, but it's an effective inductance when we have coils that are magnetically coupled. Okay, so this effective inductance will arise in these circuits, and we need to account for it. Okay, so when we see these circuits in this module and we're solving these circuits, you're going to be given the mutual inductance, and you're going to need to know how to account for it and how to solve the circuits given the mutual inductance. I'm never going to make you do all this math. I'm doing it so that you see where the mutual inductance comes from, and I think it's important. So to note that now we have VL1, which we know is clearly just going to be L1 times di dt. In this case, VL2, the voltage across inductor 2, is equal to the mutual inductance, right? Not the self-inductance, but the mutual inductance of coil 2 resulting from the current I1 multiplied by di1 dt. Okay, so you can see that this term should be an inductance because it's a voltage and it follows the same form as this equation. Just so happens that this complicated term here is the mutual inductance. Okay, so I'm going to go ahead and end this video here. This is the derivation of the mutual inductance, basically of coil 2 as a result of current I1. In the next video, or the next couple videos, I think it's just going to be the next video, I'll rederive this going the other way, where I derive the mutual inductance of coil 1 if we have a current I2. Okay, so it's basically the same derivation, but going the other direction, and I'm going to cross this source out and have a current I2 here. Okay, so I'll end this video. I know this one got a little bit long, but we'll see you guys in the next video.